Hi, I'm Professor Bertozzi with the WPI Robotics Engineering Program, here today to begin a series of videos on linkages. Linkages are ubiquitous in robotics engineering, and learning how to use them effectively is very important for a robotics engineer. So in this first video, we're going to explain first exactly what a linkage is, and then we'll talk about how to determine what the lengths of the linkages should be, where the pivot point should be, in order to determine a design goal for a certain position and orientation of the mechanism. We're going to first begin with a graphical method for determining those locations and lengths, and then we'll apply a method called a method of instantaneous centers, which allows us to determine velocities at different points on the linkages in different orientations. So let's begin by introducing what exactly a linkage is. Simply put, a linkage is an assemblage of bodies, or links, that attach to each other with joints. Oftentimes you'll see links shaped like the one shown here, but they can really take any shape. The joints allow the links to freely move with respect to each other, either by rotating or translating. A number of links attached to each other by joints is referred to as a kinematic chain. Kinematics refers to the study and analysis of moving mechanisms without respect to the forces that cause them. A simple example of a linkage would be a 2-bar, which simply has two links attached by a joint called a revolute joint. The pliers shown here are a great example of this. A 3-bar truss is shown here. Intuitively, you can see that this linkage won't move. It is actually a structure. Very commonly, though, you'll encounter what's known as a 4-bar linkage. As the name suggests, these linkages are composed of 4 separate links. Perhaps the most common configuration of a 4-bar would be a linkage with 4 revolute joints, as shown here. Typically, one link will be fixed in place and is referred to as the ground link. The motion of this linkage can be controlled with just one actuator, as represented by the motor in this diagram. This driven link is also referred to as the crank. This link on the other side is referred to as the follower or rocker, due to its rocking motion as a result of the crank's rotation. The link that joins the crank and the follower together is referred to as the coupler. Four-bars can take other forms as well, such as the crank and slider. In a crank and slider mechanism like the one shown here, the revolute joint between the follower and the ground link is replaced with a prismatic joint, which only allows translational motion. There are also types of linkages that have more than 4 links. You might have something like this 5-bar, which would actually require a second actuator to fully control its motion. The reason why more or less actuators are needed has to do with the mechanism's degrees of freedom, which is something we'll talk about in the next video. This pair of locking pliers provides a practical example of a linkage. As you can see, the plier assembly forms a 4-bar with 4 revolute joints. Sometimes you may need to design a linkage to travel along some specified path, or to be in a certain position or orientation at a certain time. This can be accomplished using graphical position linkage synthesis. So imagine we have this robot that has to pick up balls or other objects and drop them into a hopper. We need to attach a linkage to the front of the robot to accomplish this. The problem is, how do we know how long to make the links or where to attach them? This is a problem that can be solved through graphical position synthesis. So as you can see in the video, there are 3 different positions and orientations that we would like the pickup mechanism to be in at different times. So we'll say that the lowest position is position 1, and then the intermediate position is position 2, and the uppermost position is position 3. And the orientation of the pickup mechanism we would like to be tilted slightly downward as you drive into the balls, and then in position 2 we want it to be tilted back so the balls don't fall out, and then in position 3, we would like it to rotate clockwise and tilt back the other way to dump the balls into the hopper. So the question is, how do we determine the length of the links and the location of the pivot point so we get this type of motion? So if we look at point A on the pickup mechanism, moves from in position 1, position 2, and position 3 to the points shown. We can draw a line connecting these points and then draw perpendicular bisectors. The intersection of the perpendicular bisectors will actually be the center of a circle or that passes through these 3 points. Next, we can do the same thing with points B, which is the top of the L, and in its position 1, position 2, and position 3 of the pickup mechanism, and again draw perpendicular bisectors. They will intersect at the center of a circle which passes through those 3 points. So now if we create links that connect to these pivot points, the first pivot point from the green circle to point A, and then the pivot point which we found with the purple circle to point B on the pickup mechanism, that pickup mechanism will now rotate through these 3 positions. So now we've done the position synthesis, and we know how long the links need to be and where the pivot point should be. And so the next step is, suppose we want to find out what the velocities would be in different orientations, or what the direction of velocity would be at different points on the mechanism.